When humans repeat a complex physical task, they naturally get faster. Muscle memory sets in, processes streamline, and the time required per unit steadily drops. But in industrial manufacturing, observing that workers get faster isn't enough. Operations managers have to translate that human behavioral trait into rigid mathematical formulas to project future labor costs. To do this, they rely on an industry-standard framework known as the Cumulative Average Time Learning Model. Looking at this historical cost data, you can see why exact projections matter. In competitive contract bidding, your labor estimates dictate your price. If you underestimate the cost, you win the bid but bleed cash until bankruptcy. Overestimate it, and you lose the contract to a leaner competitor. Yet widespread bidding failures happen constantly because professionals fall into a specific mathematical trap. They confuse the historical average time of a production run with the actual marginal time it takes to produce the very next unit. To survive a competitive bidding process, you have to deconstruct the standard learning curve model and isolate what that next unit actually costs. This graph illustrates the core rule of the cumulative learning model. Time reduction does not slope steadily downward in a straight line. Instead, it drops steeply and then flattens out, decaying by a specific percentage exclusively when cumulative production volume doubles. A doubling event is exactly what it sounds like. It is the jump from completing your first unit to your second, then from 2 to 4, and from 4 to 8. Without highly specific historical data, the standard industry assumption for this decay is an 80% learning curve. It is crucial to understand what that number means. An 80% curve doesn't mean your labor costs drop by 80%. It means that at each doubling interval, a cumulative average time is reduced to 80% of whatever it was at the previous benchmark. Because this decay is geometric, you cannot simply divide your final goal by your starting point. To project costs accurately, you have to map out a precise schedule of these doubling steps. Let's build a hypothetical production run to see exactly how this works. We'll start with a baseline where the first unit off the line takes exactly 100 minutes of direct labor to complete. When the factory produces a second unit, cumulative production has doubled from 1 to 2. That triggers our 80% rule, dropping the new cumulative average to 80 minutes. But notice the phrasing. That 80 minutes is the average time taken across both of the first two units combined, not just the second one. When production doubles again, moving from 2 to 4 total units, that 80-minute average is multiplied by 80% once more, bringing us to 64 minutes. That 64 minutes represents the smoothed-out efficiency across all 4 units produced to date. The math here is precise for finding averages, but it masks what is physically happening on the assembly line. This is where professionals make a critical error. They look at that second row and assume that because the average is 80 minutes, the second unit itself took 80 minutes to build. To expose why that assumption is fatal to a bid, we have to look past the averages and calculate the cumulative total time. For Unit 1, 1 unit at a 100-minute average equals a total time of 100 minutes. For the second benchmark, 2 units at an 80-minute average means the factory has spent a total of 160 minutes operating. To isolate the exact time it took to build unit number 2, you take the total time for both units and subtract the time already spent on Unit 1. 160 minutes minus 100 minutes equals exactly 60 minutes. The gap here is substantial. The learning curve model reports an 80-minute average, but the marginal time required for that specific second unit was actually 20 minutes faster. If a client asks for a quote to build a second unit and you price out 80 minutes of labor instead of 60, your bid will be artificially high and you will likely lose the contract. Finding the true incremental cost of any production run means you can never rely on the average column alone. You have to calculate the absolute totals, then subtract the difference. In heavy manufacturing, companies rarely track costs unit by unit. They track them in large batches. Fortunately, this subtraction logic scales perfectly to batch-level costing. Look at this table. If management needs to isolate the labor cost for only their most recent production batch, specifically units 5 through 8, we apply the same rules. First, we find our total time ceiling. We take those 8 total units and multiply them by their cumulative average of 51.2. That gives us 409.6 total minutes of labor. Next, we establish our floor by finding the cumulative time spent just before this batch started, which was the end of the 4th unit. 4 units at a 64-minute average equals 256 total minutes. Now we simply subtract the floor from the ceiling. 409.6 minus 256 isolates exactly. Let's test this framework against a real-world scenario. This is the AeroSub fact pattern, a standard assessment for evaluating a spacecraft parts contract. We have 3 inputs: an initial requirement of 10,000 hours, an 80% curve, and a target of 8 units. Our objective is to find the cumulative direct labor hours upon completion. To get there, we must map out the doubling sequence from 1 to 8. We take our 10,000-hour baseline and multiply it by 0.8 to reach Unit 2. We multiply by 0.8 again for Unit 4 and a final 0.8 for Unit 8. 3 geometric steps bring our final cumulative average down to 5,120 hours per unit. To calculate the final project bid, we simply take that average of 5,120 hours and multiply it by the 8 total units. The result is a precise 40,960 hours. The complexity of the forecast resolves into 3 geometric steps once the doubling rule is applied. However, this mathematical precision does come with a significant practical limitation. Out in the real world, the exact shape of a process's learning curve is rarely known before a project actually begins. Hard empirical data only surfaces after the production lines are already moving and capital is spent. Because companies are forced to bid blind, relying on that 80% assumption serves as a proven, risk-adjusted industry default. It is a solid baseline, but context dictates the variance. Highly automated, machine-driven processes leave little room for human improvement, often flattening out at a 95% curve. Conversely, highly complex, manual technical tasks might see massive efficiency gains, dropping to a steep 70% curve. Ultimately, the learning curve model is not a crystal ball. It is a structural framework designed to prevent disastrous pricing assumptions when scaling up operations. Operational mastery combines mathematical manipulation with an understanding of the unpredictable variables on the factory floor.